Okay, so I want to move on looking at the second of the kind of examples or case studies, if you like, vastly different to the first. And again, the first was based on work that Lou Wankel has done. The next cases are work that I've been a part of. So this baseline estimation, motivation, we have a project, we've had a few projects actually, that are looking at utilizing large building HVAC systems. So the next case study that I'll talk about is looking at residential air conditioner. This one is building a large building air conditioner. The idea being that there's sufficient thermal mass in a large building that you can perturb in our case we're looking at perturbing the fan power without having any impact, any perceptible impact on occupant comfort. But by doing that, you're moving load around, and in moving load around, you can exploit that to provide grid services. Things like regulation service, so the signals that are coming from automatic generation control can be incorporated into controlling building loads to some extent. But the critical challenge in implementing such demand response is to estimate what the power consumption would have been if there had been no demand response action. So that's needed to determine if the requested control action has been enacted, because the utility is going to pay on the basis of that control action. So there's financial settlement aspects associated with this as well. And there's problems referred to as determining the counterfactual baseline. We'll just talk about the baseline. The sort of experiments that we've been doing are to implement, so the blue line shows the background fan power for a particular building on our campus. And then we tinker with the set point, temperature set point across the building. So the occupants all set their room thermostats to a certain value, but we have an override and increase that plus or minus a degree Celsius. That impacts on the fan power, and what's shown here is the impact that has. So there's, in this particular case, we initially reduce the temperature set point by a degree Celsius, actually, so it's in the US, so it's 2 degrees Fahrenheit, but I don't know what Fahrenheit means, so I'll just talk about Celsius. Anyway, we reduce the temperature set point. That causes the fan to work harder, it takes in more power, and then we reverse that process, so we then increase the set point and see the power drop off, and then we return everything back to normal, and there's a settling period that happens. So that's an actual measurement of implementing that control in the morning, and then in the afternoon we did the reverse process of initially increasing the set point and then reducing the set point and letting it settle. So that's what these measurements from an actual building look like, and what we want to be able to determine is what would have happened if we had not implemented that set point change. So the process that we've been utilizing is called tensor decomposition. Tensor decomposition is an unsupervised data analysis method that can find the dominant patterns across multiple dimensions. And the multiple dimensions are time, over time, fan, we have submetering data on a number of fans associated with each particular building, and day. And then tensor completion is a closely related problem of imputing missing or unobserved values. So what we want to be able to do is say, let's use this tensor decomposition idea to build a model and then say that this piece here is missing. Now, can we use tensor completion to fill in that missing information? Okay, just minor detail. So the important thing is this tensor completion idea. The process that's used is this generalized canonical polyadic tensor decomposition, if you're interested in that. Okay, so the fan power that's being measured is arranged in this three-way tensor of time times fan times day. This is the structure of the tensor. So here's the fan. So each of these values is the power, and here's the fan and the time, and then this other axis is the day. So we can take a slice through this. We get this fan time times fan slice, and it's this three-dimensional tensor. The general idea is to think about singular values. You can, if you have a matrix, you can decompose that into singular values. In a tensor, you can do a similar kind of decomposition, analogous to singular value decomposition. Okay, so having done that decomposition, we can then rebuild an approximate tensor. So we use the data from the S minus 1, all but one of the days that go into this are baseline days. So no testing is done on a baseline day. This is just how does the building behave normally. And then there's the one event day that we include in the tensor as well. The baseline power within the event window of the event day is treated as missing data. So we have, for that event day, we have all of the information that's shown in blue, but the red information is now treated as missing information that the tensor completion process will seek to fill in.
Excuse me, Ian. I have a question. How do you choose the non-event days?
Oh, in our case, that's easy. We just don't organise an event on those days. So,
okay.
So we have, I think it's now 10 buildings that are telemetered across campus. And then we will just have periods where we're not doing any testing and just measuring what the normal baseline looks like. And then we'll do repeated tests on, and then look at similar days, similar times, that kind of thing. Yeah.
Do you flag when you've created an event, or do you let the machine try to figure out whether you have or haven't created an event at that day or half hour?
So in the process that we're using here, we know when we have had an event and we want to utilise it. So we provide that information, and then we're wanting to estimate what would have happened if we didn't do the event. But you know, there's sufficient information in an event, typically, that you could use techniques to detect that as well. But we're in control of the events in this case. We know what days we're doing, what days and times we're doing it.
If we were to roll this out to the real world, we obviously don't know when the events are, so we'd need to detect them. Yeah.
Yep. The other thing that we don't know, actually, is just minor details, but what's the settling period? We know when we put the step on and down and so forth. We know that point there, but what's settling? How long does it take for this process to settle back to normal? And so I guess in a sense we can eliminate or say we're missing more data than is actually the case and use the estimation process to fill that in. But we know when the event happens, but we don't know how long it has an impact on behaviour. Okay, so the tensor entries are obtained by approximating the known entries with this low-rank tensor. And so, like I mentioned, it's kind of think singular value decomposition, and if you have a whole range of, when you order the singular values, often you find that there's relatively limited information in a matrix, that you might have a few dominant singular values and you can throw the rest of them away and not lose too much information. It's the same process here, that the original tensor is close to something that is composed of just keeping a few of the low-rank tensors. Determining how many to keep is another question, and there's open questions on that as well. So we're just saying we're going to keep R, but is R3 or 5, or that's, that depends on the data. Okay, so what does the outcome of that look like? So what we did to test the accuracy was, rather than saying, okay, we're going to utilize this to determine the baseline on an event day, it was a non-event day, so we knew exactly what did happen through that period, but we threw that information away as if there was an event there, and then used the tensor decomposition ideas to rebuild that information and compare the approximation with what the truth was. And so that's what this is showing here. It's doing that comparison. So in terms of the data, we have 1 minute data. And when we utilize the 1 minute data, there's a lot of spiking that's going on in the data. So then we can smooth that over 5 minute intervals or 15 or 30 minute intervals. And that gets rid of a lot of the spiking. What we found was 15 minute interval data. So it's just taking the 1 minute and then just summing them up over the 15 minute, averaging over 15 minutes. Gives a much closer representation of the behaviour. So this is sort of the best possible estimation. And so you can see it's not perfect. Here's the two yellow periods are the event periods, and you can see it's giving relatively good approximations. It's capturing the main influences. That's an approach where we're using lots of data coming in over lots of baseline days to be able to utilise that. To extrapolate that into actually providing services to the grid, there's still a lot of work that's required. We're just dealing with testing the building, looking at issues such as the efficiency of the energy flow into the building and back out of the building at the moment. But to implement something from a utility point of view is still some distance away.
That's a quick question there. So you used data from previous days and whether there was event or non-event. Did you take into consideration days with the similar temperature characteristics into the pre-selection of what to use for the baseline?
So we don't. The features that we're looking at don't include the weather conditions. It turns out there's not actually a strong correlation with the weather conditions.
There was a few years ago, United Energy in Victoria ran a number of tests to provide demand response to voltage reduction. And of course, well, they had to estimate a lot of things and have a baseline because they wanted to sell these services to AMO as a RERT. So how much? So AMO was keen, and the usual standard for AMO is to ask them to use an average of the previous 10 days. That turned out to be very unreliable. So they settled on using the previous 10 days with the same temperature characteristics of the day that they provide in the event, and the data seem to show that work more reliable. So
right.
That's an interesting.
Yeah. So I guess climatically,
It's just load as a bulk, so it includes all kinds of things. But it's not a specific application like this one.
It sort of has surprised me that there's not a greater correlation with the weather. And I guess one of the things is that the test that we're doing is plus or minus 2 degrees Fahrenheit, which is it's a very small perturbation in a sense on the total fan power. So there's nothing to prevent building ambient temperature, humidity, those kinds of things into this same process. We have a 3-dimensional tensor, but you could expand that out further. So.
Just a clarification, you said you do this in 10 different buildings, is that right? Do you use the data from the different buildings as, say, panel data or anything like that to see if you aggregate it, what does it look like? Is there cross-correlation or anything?
It's a stage process. At the moment, basically all we're doing is just setting up a bunch of tests and trying to understand the dynamics of the HVAC system The motivation behind all this was some testing that we originally did at Los Alamos National Lab, which showed when you think of a building as like a battery of energy in versus energy out, it's about 50% efficient. And so it sort of begged the question, well, why is that the case? And so we're really more kind of exploring using measurements and then trying to build some models to explore what's the physics going on there, and then how's that impacted by different types of buildings. And so we have these 10 buildings telemated.
Diversification would be an interesting
Yeah.
for the market operator or the network operator.
Yeah. So to actually provide a service to the grid, and the university is not interested in doing that at the moment, but to provide a service to the grid, then you could really start to look at control schemes that we're utilising the 10 different buildings, and if you needed to do some load shedding over a longer period, you could stagger the buildings to achieve that and things like that. But that's not been the goal of our work so far. Okay, so the next is another next case study is another estimation problem. In this case, what we're wanting to do is, and it comes from one of the students in Michigan, a PhD thesis. I was not the advisor for the student, but I was on the student's committee. So he did all the work. So what we wanted to be able to do is to estimate what given a measurement of the feeder load, so at the substation, try and disaggregate the power consumption of residential air conditioners on that distribution feeder, separate that off from all the other load. So why is that important? Well, in another project that we're doing, we're looking at controlling large numbers of residential air conditioners to provide grid services. And so we want to be able to know, if I'm wanting to provide a control action, how much controllability is available on that feeder. As I mentioned earlier, it's the gain in the control loop. The other sorts of things that you could do with this, in the US at least, there's this issue called fault-induced delayed voltage recovery that happens because most of the residential air conditioners are single-phase induction motors that are prone to stalling, and when they stall, they kind of lock out and there's some issues that arise. So you could use these ideas to, again, estimate the amount of air conditioning load and look for vulnerability to this FIDVA stuff. You could use these same ideas, I think, for if you wanted to disaggregate rooftop solar from from the demand on the feeder as well. Okay, so the total AC power could be obtained by placing sensors on each device, and in a sense smart meters kind of provide that, but at a relatively slow update rate. To put sensors everywhere is expensive, requires communications, there's privacy issues. So what we've been, the focus of this is to say, can we just use SCADA data coming from the substation along with knowledge of the physical system, so we have real-time information coming from SCADA metering, and we have knowledge of the system, and using that, can we do this disaggregation? So the algorithm that we use is called dynamic fixed share. It separates out residential air conditioning from all the other load. At the feeder level, keep in mind the air conditioning load is these large numbers of small loads, each one of which is undergoing thermostatic cycling. So when you do this separation, we'll go through how this all works, but this is the sort of information. So the total load is this pink, the other load is the yellow, and the air conditioning load is the blue. And so that's an outcome of the disaggregation. To actually explore that process, so the online aspect of disaggregation, it's just using the feeder demand measurement through this algorithm, dynamic mirror descent algorithm, DMD, which we'll look at very briefly, to provide an overall estimate of the air conditioning load. So we're not using any measurements along the feeder, only the measurement coming from or measured at the substation. So that's the online part of it. But there's an offline learning part as well, where using historical load data and patterns of models that we develop. So in this case, we are using the smart meter data together with historic measurement of the feeder data to build and to develop models that go into a bank of models. So the general idea is, in an offline setting, we build a number of potential models to represent that feeder, or to represent the behavior of the air conditioning, aggregate air conditioning load and the other load. Those models are developed in this offline setting, and then in the online setting, this DFS, dynamic fixed share algorithm, assigns weights to the different models, the weights being assigned more influence to those models that are providing a more accurate assessment. So the models used to create a variety of different modelling structures. So we use historical device level measurements along with historical feeder and weather data. Two types of regression models used for the prediction of the other load demand, a time of day regression and a multiple linear regression. And I won't go into much detail about either of those, just to say there's these two models that are used for other load. And then for the AC demand model, there's three different models that are used for that. One is a multiple linear regression model, and it's using the time of the week, the lagged outdoor temperature raised to the power 1, 2, 3, and 4. So there are 5 features in this regression model. So the three different types of models. The regression model, there's a linear time invariant model and there's a linear time varying model. The linear time invariant model just says we have two-dimensional state space. One state gives the proportion of the total number of air conditioners that are in the on state and the other proportion that are off. And then it's the state transition matrix, is a transposed Markov transition matrix, just capturing the transitions between the on states and off states. And then it's indexed dependent upon ambient temperature. So this is the structure, but you can see there's this M index. There are M different models, and each one has different parameters in the A matrix, which is describing different transition rates that are appropriate under different temperature conditions. Okay, so there are LTI type models and a range of LTI type models dependent upon the ambient temperature. And then the time varying models are same structures, the linear structure, of course, but then the A and the C are varying in a time response. Well, the one model is varying with ambient temperature. So if we go back to the previous case, there are different models for different ambient temperatures. In this case, there's the one model that is time varying dependent upon the ambient temperature. Okay, so there's these three different types of models for AC load. There's two different types of models for the other load. These models all get implemented using this dynamic mirror descent algorithm. And without going into any of the details, this is the DMD algorithm, which is on a model basis. So there's, for every different model, this convex optimization problem is being implemented. This is L is a loss function, so it's a gradient descent form of algorithm. So every model is being driven to its kind of best set of parameters. And then the dynamic fixed share is the second part here, which is then saying, well, all of these models we need to combine together. We want to combine them together in a way that it gives me the sort of the best outcome. And the best outcome means the sort of smallest value for the loss function. And so that's what this is doing. It's then combining for each model, it's determining a weighting, and then it's combining through the weights all of the model outcomes into a single model outcome at time t+1. So this process here is dynamically adjusting the weights between the different models. And I'll show a figure of what that looks like. This is the outcome of that. So the AC demand, the actual AC demand versus the estimated AC demand, and it is quite close. This is the other load, it's quite close. This is the total demand up here as well. So I won't spend any time except to say it works fairly well. It's not perfect, but it works fairly well. And then the evolution of the weights is shown here. And again, without going into any of the details, you can see that the sort of the best model combinations show up pretty rapidly or show up pretty well. Everything is initial, all of the models are initialized to be of equal weights. So that's what's happening up here. And then this is also the other models drop down to 0 as the preferred models pick up the maximum weights. Okay, starting to sort of rush like a fire hydrant or drinking from a fire hydrant or whatever the saying is. So maybe we won't even get to the last part, but the next thing I wanted to talk about was this cluster-based idea of chance-constrained optimization.
Excuse me, Ian. Can I ask a question?
Yeah.
How do you choose to use those three models in your work? Because you said you used multiple regression and then LTI, LTV.
Yeah, so all of those models, the whole ensemble of models are being evaluated here. And then, so this is seeking to drive the loss function to a minimum. And then, depending on that residual loss, so if I have a bad model, it will give me a high value for the loss, and then that will drive the weight to a small value. If the loss function, if the model is particularly accurate, then that'll show up in small values for the loss function, and that will drive the weight to a high value. So it's this. So the process itself is looking after. I run all the models independently, but then when I combine them together, it's saying this one worked really well, this one didn't work very well. And so it's dynamically weighting that. Okay, just some background to this problem. We're looking at energy hubs which have wind, solar, some gas supply, but we want to minimize the amount of gas that's utilized. We have battery storage, hydrogen storage, electrical load, heating load, and all sorts of other combinations of possibilities. The optimization background, because we're dealing with wind and solar, there's uncertainty in that. And I won't go into all of the details, but it turns out to be a chance-constrained optimization problem. What we wanted to do is this cluster-based energy hub design. So we end up with a problem of this form. It's a chance-constrained optimization. We're satisfying the constraints with a certain probability. We're not saying that they have to be deterministically satisfied. So we have this combination of random variables, decision variables, and then there's a pre-specified probability of violation. Solving that problem is a computationally challenging problem, and there are some other issues that arise as well. So it turns out to be advantageous to translate that problem into a robust optimization problem. But a robust optimization problem has some issues as well, in that it can become very conservative. And so the message is, in terms of minimizing the conservativeness comes about through, we take a large set of scenarios of wind power and of solar power and of load, and then we want to use that set of scenarios to establish a probability space. And it turns out that that probability space becomes, we then have to be robust across that probability space. So that becomes a troublesome, and to go into the details would take too long. But what we can do is, instead of saying, well, let's look at all of these scenarios of wind, solar, and load as being independent, let's look at clustering those different groups of scenarios. So if you think about weather patterns, at particular locations there are probably dominant weather patterns. And so we can cluster around those dominant weather patterns. And then rather than having to satisfy our optimization having to be robust over a large space, we end up with having to be robust over a number of different smaller spaces. And the process for clustering that we used is this principal component analysis, which I won't go, well, it's doing a singular value decomposition, determining from that what the principal components are, so the dominant singular vectors, and then using that to establish the clusters. That then turns our optimization problem from where we had a single chance constraint or probabilistic enforced constraint into one associated with each of the clusters. And then we can work with that to obtain a solution that is much less conservative. And just to show the difference, for one cluster, the cost for this particular microgrid was $2.26 million. Separate into two clusters, reduce the cost. Separate into four, reduced it further. So there's a reduction in the conservativeness that arises by dividing the data up into a range of different clusters. And for the last case, we won't go there. It was to sort of motivate the idea of operator controls and guidance coming to an operator in this work through a model predictive control strategy, but one could also think about doing that through an AI strategy as well. So, my AI talk is the process, the connection is about data analysis. And for what I've been, the tools that I've been using, the machine learning type tools, it's about large amounts of data, how to manipulate those large amounts of data to provide things like missing information, estimation of or decomposition of loading, those types of things.
Perfect. Any questions or comments?
When you did this clustering and optimization, did you compare with some like a scenario generation techniques in such a way that you create scenarios that are correlated, so it's still like finding an optimization problem, but no with the clustering?
I'm not sure I completely understand.
But the whole point of the optimization was to create scenarios that, or the clustering, to create scenarios that are correlated.
Yeah.
Right?
Yep.
So if you compare this solution with normal scenario generation techniques that take correlation into account.
So doing a comparison, like if you are at a location where there are certain dominant patterns and it's either the pattern is like this or like that, then each cluster shows, takes its proportion of the total number of scenarios, and the process works well. You're capturing sort of most of the scenarios. If you're at a location where the variation in the weather patterns can be, there's not dominant weather patterns, but it could be all over the place, then you need a lot more clusters to be able to capture that. And each cluster is capturing correlation, but there's a lot more sort of inter-cluster uncertainty as to how to assign the scenario to the particular cluster. I'm not sure that answered your question. Maybe we can talk offline to explore that a little bit further.
Okay, thank you everyone, and thank you Ian for your eye-opening talk. So I think everybody has a better idea of what we are going to do and what we are going to learn throughout this course. Okay, please join me thanking Ian for his talk.